coastal aquifer in Tunisia in the frame of the Outreach Lecturing Fund of Fulbright program. In Tunisia, in coastal zone, the water resources are considered as strategic for the country since we have a population in growth, as you can see in this figure. Actually, we are almost 11 million people, and we'll reach a maximum of 30 million in 2050. And this population is increasingly urban and concentrated along the coast. And the development of agriculture, industry, and tourism, as you can see in this figure, we have drinking water. So, with development of agriculture, industry, and tourism, we have about 300 million cubic meter for drinking water. The industry is about 100 million cubic meter. Tourism, 20 million cubic meter, and agriculture, 2,100 million cubic meter. The agriculture represents about 80% of ground water use, and the other sector, drinking, industrial, and tourism, it's about 20%. In this map, we have the map of the water use in the north, and especially in this area of Cape Bon, we have a big use of water, and in some touristic place. And here we have the oil industry and gas industry. This water resource, it's very variable, and we have a variable availability of water resource. And we can see in this map of the surface water, in the north part of the country we have most in blue in the surface water, and the groundwater, it's located more in the south and the center of the country. And this water resource, it's limited to about less than 400 cubic meter per capita and per year, and it's not uniformly distributed in space and time in the country. And it's largely exploited. About 80% of the ground of the water resources are exploited. This water resource, it's also variable in severe and irregular climate, which we have an increasing of water demand. And here we have the plot of the increase of water demand since 1960 to 2000. Actually, we are about 1,500 use of water, and this increase of water caused another exploitation of the water resources. Here we have the map of the overexploited aquifer. Most of the aquifer in red are overexploited, and many of them are located on the coast. And this overexploitation caused a piezometric drop for almost of the coastal aquifer, and as a consequence of this isometric drop, we have an increase in the salinity of water. And here we have the map of the salinity of aquifer, and the aquifer in red have salinity more than 3 grams per liter. What's the cause of the salinization of aquifer? Of course, we have natural and anthropogenic causes. Among these causes, we have the seawater intrusion, the dissolution of mineral through water-rock interaction and ion exchange. Also, we have the wastewater and main drainage and industrial plant contribute to the salinization of aquifer. Also, the acid rain through the surface water can contribute for the groundwater salinization increase. Some geothermal water and some main waste. What are the consequences of this increase in salinity? We have economic and social consequences as loss of fresh water and deterioration of water quality, consequences on the environment, and we have loss of biodiversity and replacement by alternative species. On human health also, in water we will have inorganic pollutant as nitrates, arsenic, selenium, boron, and in some cases radioactivity. Also loss of fertile soil, collapse of agriculture, and increased immigration and exodus to the cities. The geochemical and isotope tool used in these studies for tracing salinity are measured cation and anion, and also stable and radioactive isotopes of water molecule. Today I will present the problem of salinity in 4 coastal aquifers. In Carbon aquifer, located in the northern east of Tunisia, the Sahel of Sousse in the central part of the country, and the North Geoffara aquifer located in the south of the country. In this aquifer, sampling and measurement were performed on more than 120 samples, and the results were published in international journal for all these case studies. The climate of this region varied from the subhumid in the El Hawariya plain to the semi-arid in the oriental coast and in Sousse aquifer, and to the arid in the Geoffara aquifer. And we have a mild winter and hot summer, and average rain vary from 570 millimeter to less than 200 millimeter in the south. And as a consequence of this climate, we have no perennial river, and small river carry water, and intense storm cause surface runoff. Wet layer located in this region and wet lacerite are the major wadi reaching the coast, and these wadis discharge also salty lake called Sebha. The evolution of exploitation in this aquifer in the last decades show an increase in the number of wells and also in the exploitation of the aquifer in the eastern coast in Haware and also in the Geoffara plain, as you can see in this plot. And this increase of the exploitation have a consequence on the isometry of this aquifer, and we have a continuous decrease ranging from 1 to more than 14 meters according to the location of the well in the El Hawariya plain. For example, we have a decrease about 11% of the total volume of the aquifer, and in the oriental coast we have a decrease about 5%, and in the Geoffara plain we have a reduction of the artesian pressure and depletion of the well, and the spring will become dry. And as consequences of this drop of the piezometry, we have an increase in the salinity of water, as you can see in this time series of the oriental coastal aquifer. The geology of this region, the block diagram plotted for the carbon area shows that the deep aquifer of the Miocene and Oligocene outcrop in the Jebel Sidi Abdurrahman and in the south of the oriental coast aquifer. For the shallow aquifer composed by the Plio-Quaternary aquifer, it's occur near the coast. For the Hawariya plain, this block diagram, Hawari is this extreme part of the carbon. This block diagram shows three aquifer, a shallow aquifer composed by the Quaternary and the Pliocene, deep aquifer composed by two layers, Astien and Les Anciens. For the region of Sousse, the hydrogeologic cross-section plotted for this region show that the groundwater occurs mainly at two levels. The first level is the shallow aquifer between 20 and 60 meter depth and composed by the Neopliocene sediment, and the deep aquifer between 100 and 250 meters, more saline and composed by the sandstone formation of the Miocene. For the Jafara aquifer located in the south, we have a multi-layered aquifer composed mainly by four levels. This level, we have shallow aquifer composed by sand, Poncian sand. The second is the Miocene sand. The third level is the Senonian limestone. And the fourth one, and the deeper one, is the continental intercalaire. The continental intercalaire, it's one of the biggest aquifer in North Africa, and the exploitation of this aquifer, actually it's about 2.5 billion cubic meters, and this exploitation will be maybe at 7.5 billion cubic meters in 2015. And this aquifer is shared between Algeria, Tunisia, and Libya, and it's composed by two levels. The upper level, it's called the complex terminal, and the lower level is the continental intercalaire. Here we have a map of the complex terminal and the continental intercalaire. The continental intercalaire has a wide by 1,200 kilometers and 2 kilometer depth, and it's the first one. It's the Nubian sandstone shared by Egypt, Libya, and Sudan, and the second bigger is the continental intercalaire, and the third one is the Illumidan aquifer shared between Algeria, Mauritania, Niger, Algeria, Mauritania, and Niger. The piezometric map of the oriental coast aquifer show that the main flow has a direction from the west to the east, along the side, along the wedges, and toward the sea, except for the central part here, or the central part of the aquifer, where we have an inversion of the hydraulic gradient and piezometric drop reaching in some place minus 12 meters below the sea level, and caused essentially by the seawater intrusion. In the quaternary aquifer of El Hawariya, the piezometric map is characterized by groundwater divide. We have a flow rate coming from the south and from the north, toward the center of the plain and moved toward the east and the west. For Sus aquifer or Wedleya aquifer, we have main flow from the southwest to the northeast toward the sea. The same case in the northern Jafara aquifer, where we have this flow toward the sea, and the groundwater is recharged by the runoff, and also from vertical leakage upflow from the Jafara aquifer and also from the continental intercalaire. The continental intercalaire has a two-direction flow from the west, where we have the recharge area located in the mountain of Algeria, western Algeria, and the discharge is located in the Short Jerid and also in the Mediterranean Sea near the city of Garis. And the second flow is come from the south to the north. The salinity map of the eastern coastal aquifer show a high salinity from 6 to 8, and also in some places reaching 30 grams per liter. And if we superpose the salinity map, the piezometric map on the salinity map, we see that the high salinity consists of the piezometric drop. That means the seawater intrusion has a big consequences on the increase of the salinity of this aquifer. For El Hawaliya plain, the high salinity located in the central part of the plain, it's located near the depression area. This high salinity, it's mainly caused by evaporation and also by water rock interaction, because we have gypsum minerals in these places. Near the coast, the salinity is about 2 to 3 grams per liter, and this low salinity is protected by the littoral barrier composed by the Tyrrhenian. It's a geologic formation of the Quaternary. For the Wedleya aquifer or Sus aquifer, we have salinity varying from 2 to 10 grams, and in Jafara aquifer we have salinity from 3 to 8 grams per liter. The estimation of mixing water it's done through this conservation equation and this equation permits the estimation of the seawater fraction in the wells having seawater intrusion. And with this estimation, we can draw the map of the estimation of the mixing of seawater. And in some place, we have 1 to 30%, and we can reach 66 to 70% depending of the location of the well or of the piezometry. In some cases, we have only 3%, so we have big heterogeneity of the process of salinization in this coastal aquifer. For El Hawariya plain, we have a fraction of seawater less than 1%, so we can confirm that we don't have seawater intrusion in that aquifer. The paper diagram plotted for this 4 aquifer show that we have mixed profile, chemical profile. We have sodium chloride and calcium chloride water type. We have dominance of chloride and sodium in most of these aquifer, and where water are contaminated by seawater are turning into calcium chloride water type, and this chemical trend is different than seawater. So because the seawater has sodium chloride water type, the sodium is retained in clay mineral, and the calcium is released in the aquifer. The determination of the salinity and the origin of the salinity, it's given by the relation between the major element and the sodium chloride established for this aquifer show that this sample it's the correlation, it's positive correlation between sodium and chloride for almost of the sample, and this positive correlation indicates that we have a contribution of the dilution of the halite to the mineralization of water. So the sample was located on this line. We have the dissolution of the halite. We can also see the existence of two parallel lines. The first one is the dissolution of the halite, and the second line, the line with the sodium chloride ratio higher than marine ratio, and reflecting an income of sodium for all these sample to the groundwater system, which seems to be linked to the water-rock interaction and ion exchange, which we have ion exchange between sodium and calcium, since we have clay minerals and organic matter in this aquifer. So the sample with sodium chloride ratio less than marine ratio are affected by the seawater intrusion, because I said the sodium is retained and the calcium is released in the aquifer. The bromide-chloride relationship is one of the better relationship to estimate the seawater intrusion, since the bromide and the chloride are considered as a conservative element, since their residence time in the oceanic mesas are very long, and they are considered as a distinctive geochemical fingerprint for this seawater intrusion. The bromide ratio of sample equal to the seawater line are affected by the seawater intrusion, especially for the aquifer of Sousse and aquifer of the oriental coastal aquifer. In some cases, this relationship, it's not very distinctive, since we have maybe 2/3 of the sample ranging far of this marine ratio, about 20%, and the origin of this salinity in this case is related to the sea spray and the influence of the infiltrated rainwater, and in some cases also we have brine contamination. The processes of dissolution, ion exchange and precipitation is actively taking place in this aquifer. The relationship between saturation index versus the amount of the sodium show that we have a big sample who has an index saturation that means lower than 0. That means this water are unsaturated with respect to gypsum. That means the water can dissolve the sulfate from the gypsum and contribute to the increase of the salinity. Also, we can see a progressive saturation versus the increase in the sulfate concentration. In the aquifer of Sousse, this high salinity seems to be linked to the geology of the region, since we observed lenses of gypsum located in the clay minerals, as we can see in this XRG spectrum, and we confirm the presence of the primary gypsum in the geologic formation and contributing to the increase of the salinity. The stable isotopes and the ionic and geochemical study done separately. It's not distinctive, but when we do a combination of these two approaches, it's more explicit. The plot of the oxygen 18 deuterium for these 4 aquifers show the presence of 4 groups. The first group is located aligned on the seawater intrusion line, and we have a confirmation of this seawater intrusion. The second group, it's located between the local meteoric water line of Tunis-Carthage rain station and the global meteoric water line. This group has a concentration of oxygen 18 very close to the weighted average rainwater. So all of this group are coming through the recharge from the rainwater. The third group has an isotope composition far from the weighted average of Tunis-Carthage rain station. So in this group we have a fingerprint of all the water, since we have a very depleted water sample in comparison with this group. The fourth group is composed by water from the Jafara and continental intercalaire. The isotope composition in this group, it's very depleted, and it's represent paleo water, and the recharge in this group have been in climate different than the actual climate. The relationship between chloride and oxygen 18 can replace the sample between 2 poles. The first pole is the pole of seawater with 0 per mil of oxygen 18, representing the standard mean ocean water, and chloride composition about 19,500 milligram per liter. The second pole is the pole of the Tunis-Carthage rain station, minus 4.4 and 10 milligram per liter for rainwater. The samples located between these 2 poles are affected by the seawater intrusion and the evaporation. The second group has a concentration in chloride between 300 and 2000 milligram per liter. The origin of the salinity for this group, it's related to water-rock interaction and cation exchange. For the old water, we have fresh water. The composition in chloride is between 100 and 400 milligram per liter. And for the paleo water, we have composition from 1,000 to 3,000 milligram per liter. And in this group of water, the salinity, it's mainly caused by the dissolution of the halite mineral. The use of the tritium can also distinguish the different origin of the salinization. For the oriental coastal aquifer, we have the tritium can identify the water type. We have the first group composed by the post-nuclear pole. We have a high content in tritium unit. For the low content of the chloride, we have a fast infiltration, and these samples are located near the rivers. And for the group of recent water, we have recharge during the last decade, and also we have a high salinity in comparison with this group. For the old water, we have a low amount of tritium and also a low content in chloride. The tritium and the carbon-14 can also be used for the estimation of recent or old